So, let us consider an example 1. Let us say that you have a system with mass and pulley and string, the kind of system that you always love to deal with in mechanics problems. So, we start with such an example because it will have a good transition from your earlier studies in mechanics to the mechanics of fluids. So, where we make a change is like we put some fluid, say oil, in the narrow gap between the block which is there on the plane and the plane. So, this qualitatively is a narrow gap of say height small h. Let us say that mass of this is m1 and the one that is hanging is m2. We make further statements that it is this pulley is massless and frictionless and also this string is inextensible. Assume that the fluid which is there in between the block and the plane is Newtonian with a viscosity mu. Our objective say is to find out what is the velocity of this block of mass m1 as a function of time. So, this is the question that we would like to answer. Okay. This is a very simple problem, but we will try to go to as much fundamental depth as possible for such a simple problem. We may start with the expressions and you will see the expressions are very intuitive, we may write those easily, but we will start with the free body diagram of different elements which are present in the system to have a more thorough insight on what happens. Let us draw first the free body diagram of the pulley. Okay. Most of the times you will never draw it, but if required we should. The pulley is hinged to this surface. So, the center of the pulley, at the center there is a hinge. Now, what should be the forces which are acting on this? Normal reaction, if you say normal reaction by whom to whom? Okay, let one by one. So, first say we are talking about the hinge. So, what type of reaction you expect for the hinge? So, there are contact forces, it is something which is occurring in a plane. So, in general you will be having general force in a plane which may be resolved into two components. So, let us say that we are talking about two components Cx and Cy, which are like arbitrary orthogonal components of the forces which are there at the hinge. Then tension in the string. So, here you have some tension T1, here you have some tension T2. For the time being, let us forget about these assumptions which have been given: massless pulley, frictionless pulley, inextensible string. and then we are not exactly using the consequences of these in drawing the free body diagram. So, in the free body diagram we are keeping everything as general. So, let us consider that the pulley might have a mass also. So, just to see that if it has of course it has a mass, when we say massless we do not mean that it is literally massless, we mean that effect of that is not significant, that is all. So, whether the effect of mass is significant or not, how will we understand? These types of statements are very important, like massless, frictionless, inextensible and so on. Most of the times you think that these are for beautification of the problem statements, and at the end you come up with a conclusion which sort of abstracts you from the path by which you have come to the conclusion. For example, if we say T1 equal to T2, right, we will of course see T1 equal to T2, all of you have learned from your mechanics that it should be like that. Now, can you tell that whether T1 equal to T2 is because of massless pulley, frictionless pulley, inextensible string or what? See, now I am getting 3 different answers from. So, like if it is a multiple choice question, massless, frictionless, inextensible, all the above, none of the above, or many choices are given to you. Let us see which one is the fundamental and which one is dominating. So, if you think that the massless is the thing that should be put in question, so let us consider that it has a mass and see that what is the consequence. It will help us in understanding that what would be if it is massless. So, let us say that MP is the mass of the pulley, so it has its weight also, okay. Now, what we do is we want to get an expression between T1 and T2. So, if we take moment of all forces with respect to C, the 3 Cx, Cy and Mg, these get cancelled, it helps us in obtaining a relationship between T1 and T2. So, what is that basic equation that we are looking for? Resultant moment of all forces with respect to an axis passing through C perpendicular to the plane of the board is the moment of inertia of this pulley with respect to an axis which is the same as the axis with respect to which you have got the moment times the angular acceleration. So, if say capital R is the radius of the pulley, then you can write this straight away as T1 minus T2 into R. If it is the pulley is like a disc, as an example, say if we call it half m r square, right. So, if the mass of the pulley is neglected, then automatically it will give rise to T1 equal to T2, right. So, it does not matter whether it is frictionless or not, so far as this goes. Is it a totally correct statement? Now, another question I am asking you. You should try to understand it through a contradiction. Say you have encountered cases where you have a pulley with a string or a belt around that, and there is a difference between these tensions, and the difference is given by, say, if it is an impending slip, T1 by T2 is e to the power coefficient of friction into the theta angle of wrap. This you have learnt in the statics. So, now I mean here we are seeing something different, right. So, what is the anomaly? You think about it, I will ask you next time. Let us continue with this problem, because for this particular problem that is not going to be important, so much I can tell you. Now, we come to say the free body diagram of M2 maybe. So, you have the weight then you have the tension which is T2, of course T2 is equal to T1, and then if the system is released, what would be the direction of motion that you expect? So this is coming downwards and this is expected to go towards the right. So understand the physics of this problem, when it is moving downwards it is tending to go towards right, there is a resistance at this interface which does not want to make it go towards the right so easily. So it is somewhat like a friction, and that friction here is sort of lubricated, it is not a direct contact between two solids but there is a thin film of liquid in between. So that means if that is the case, then if it comes down, let us say it comes down with an acceleration a. So if this comes down with an acceleration a, which is, you may say this a is like dv2 dt. So when it comes down with an acceleration a, you expect that m1 also moves right towards right with an acceleration a, again by which assumption it is there? Inextensible string. So inextensible string had a role to play here, massless pulley we have seen had a role to play here, and yes, frictionless pulley also has a role to play here because the belt is being wrapped around the pulley and because of friction there may be a difference in the contact forces between the belt and the pulley. So that will be more apparent if you draw the free body diagram of the belt and see its interaction with the pulley. So when you are thinking of interaction between the belt and the pulley, that is not considered here, and that is not considered implicitly because it is frictionless, so important interaction is through friction. Normal reaction will always get nullified even if it is considered because you are taking moment with respect to the center. So all these have been used in some way or the other. Let us draw the free body diagram of M1, which is the important matter so far as the understanding of viscosity goes. So if we draw now the free body diagram of M1, now you tell what are the forces which are acting on M1. Yes, one is T1, there is some normal reaction to the, what is the origin of this normal reaction? This is not a direct contact between the solid boundary and the block, yes, there is some fluid is there and there is a pressure distribution at the interface between the fluid and the solid. So the resultant of that pressure distribution gives rise to this normal reaction. Of course the same normal reaction we have drawn, but we have to understand that physically where it originates. Then there is some resistance also. So what is the resistance? There is, let us call it F, just with analogy with the problems involving standard mechanics of solids. So this F is sort of friction force, but here again the origin is not the direct contact between the plane and the block. So what is the origin of this friction force? Viscosity, right? So it is viscosity or viscous effects at the interface between the block and the fluid. So that should be expressible in terms of the shear stress, and the shear stress is expressible in terms of the rate of deformation through the Newton's law of viscosity, because we are assuming it is a Newtonian fluid. So what we expect here is that this should be some equivalent shear stress at the interface times the area. So let us say that A is the bottom surface area of the block. So that is another input to the problem. Now only work that is left is to relate the tau with the rate of deformation. Now the rate of deformation is something which takes place where, which takes place if you look at the magnified view of what happens in this thin film. So, in this thin film you see that there is a solid boundary at the bottom which is stationary, at the top there is a block that is moving. So, this is the block. So, this block is moving with a particular velocity, and this is like this block is idealized as a particle. So, when you idealize a sort of rigid body as a particle, when you do not have rotational effects, the fundamental difference between a particle and a rigid body is a rigid body has rotation, or it is capable of having different rotational components, but particle cannot rotate. So, this of course we are not considering that this could rotate in this type of situation. So, it is just like a particle or a point mass. So, everything is moving towards the right with a particular velocity which is changing with time. So, let us say that this has the velocity v. So, when this has a velocity v, of course that is a function of time that you have to understand. Now, if you draw the velocity profile at any section which includes the fluid between the block and the plane, at the wall because of no slip boundary condition it is 0. Here what should be the velocity of the fluid? It should be v, that is also because of no slip boundary condition. So, no slip boundary condition is not 0 velocity of the fluid, but 0 relative velocity. So, if the solid moves with that velocity, fluid will also move with that same velocity. Now, see the catchword, again a very nice catchword is there is a narrow gap. So, narrow gap means this thickness h is so small, it is so small that this variation of velocity between 0 to v may be assumed as linear. Okay. Now, if you see that this shear stress, let us now complete the expression for the shear stress, it is mu times the rate of deformation. Rate of deformation could be different at different y locations, but if it is a linear profile it is same everywhere, because rate of deformation is related to du dy that we have seen. So, rate of deformation in such a case is du dy, where u is the velocity. So, if u versus y is a straight line, du dy is a constant. So, this for our present case will become v by h. So, remember what are the approximations or simplifications which have led towards this. If this is not a narrow gap, it has to be what is the rate of change of u with respect to y at the interface between the block and the fluid, not at anywhere, but since now it is a straight line, it is as good as it is anywhere. So, the very important understanding is we are using that tau equal to some mu, it is better to say that it is a partial derivative of u with respect to y, because u could be function of many other things. Here of course u is a function of time, but no space coordinate, so still it is like a partial derivative. If you write du dy, which we wrote for the first time when we wrote such an expression just for simplicity in understanding, but it is in general a partial derivative. It assumes that there is only one component of velocity, and the partial derivative comes from the fact that that one component of velocity itself could be a function of many things, x, y, z, time, like that, and it could itself be a variable. And what is y? The important thing to keep in mind is that if you have a solid boundary, y is the coordinate which is normally directing outwards from the solid towards the fluid. So, y is a generic thing, it is not that any y axis you define, it is that du dy. So, this y has a special meaning, this y is the axis which is normal to the surface into the fluid that we are considering. So, if you are having a different type of coordinate axis, then you have to adjust this with a plus or minus sign. So, that you have to keep in mind that this is the orientation that we had considered for describing the Newton's law of viscosity, that sanctity should be preserved. With that understanding, now we write the equations of motion by Newton's second law, which should be straightforward. So for the block M1, of course along the y direction it is equilibrium, so n equal to mg, that is not a part of the requirement of the problem. So we are just writing the resultant force along x for M1 is equal to M1 into the acceleration of A, that is A1, that is nothing but dV1 dt. So resultant force along x is T1 minus F. Since it is an inextensible string, we will have V1 equal to V2 equal to V. So very soon we will write in place of V1 as V or V2 as V, where V is the common velocity with which the system is moving. So you can write T1 minus mu V by H into A is equal to M1 dV1 dt. Let us say this is equation number 1. We write next the equation number 2, which should be for the mass M2. So let us draw the free body diagram of the mass M2, or that is already there, so we just write its equation. So it is now along y we are considering. So this is coming down, so M2g minus T2 is equal to M2 dV2 dt. From the inextensible string we can write V1 is equal to V2, say equal to V, and we have already seen T1 equal to T2. So if we call this as equation number 2, in equation number 2 we have this T2 same as T1. So we can get what is the expression for T1 and substitute in equation number 1. Let us do that. So from 2 we get T1 is equal to M2 dV dt, sorry, T1 is minus M2 dV dt plus M2g, and that we substitute in 1. So minus M2 dV dt plus M2g is equal to that is T1 minus mu V by H A is equal to M1 dV dt. So you have M1 plus M2 dV dt is equal to M2g minus mu V A by H. It is very easy to integrate it, you can just separate the variables. So you bring this whatever function of V is there on one side and whatever function of t on the other side. So you have dV divided by M2g minus mu V A by H is equal to so you can integrate it with respect to time, say at time equal to 0 the velocity was 0 or V0 in general, maybe if it was having an initial velocity, and at time equal to t say the velocity is V. So you can from this if you integrate you will find an expression for V as a function of time. Of course in an exponential form it will come because it will be in a logarithmic form the integral that will appear. So it will be some function of time, and if it is released from rest, it should, its velocity should increase with time or decrease with time? Increase, right, because the m2g that is falling down and making it to move towards the right. At the same time there is a viscous resistance, so it will come to a sort of asymptotic state when it has a balance between these two forces, and then there is no further change in velocity. So without working it out, maybe the velocity versus time characteristic could be something like, maybe like this, and let us say that it comes to a sort of steady state at some time which is large time, theoretically tending to infinity, practically large time. So what should be this velocity? So can you tell that what should be this velocity? Yes, m2gh by mu a. So this is, and the reason is straightforward, that when you have a steady state, this there is no more change of velocity with respect to time, and therefore it should be an equilibrium between these two forces. So that would give rise to this type of expression. So whenever we work out a problem, it is important that we also try to get a physical feel of what is happening, try to formulate it in terms of the physical feel, try to get a sketch maybe of what is the variation, and then it will be so easy to interpret whatever results you are getting, whether they are correct or not, or whether they are having some physical sense or not. Okay, with this we will have a short break, and then we will continue with the discussions on viscosity and surface tension in the next part of the lecture. Thank you.